Today is another one of those topics which are only mildly related to statistics, but very interesting. And I promise you it'll be very colorful. So let's get to it. We're going to start off with a topic called bifurcation. In bifurcation, we'll use this to illustrate it, we'll use this what's called the population or growth equation. And the idea here is that insect population growth, xn plus 1, is the population, the fraction of maximum. Take the maximum, find what percent of the maximum. So x is a percent, actually a decimal between 0 and 1, of the maximum number of insects which can exist at time n plus 1. It's a function of how many insects were there the year before at time n. So if x is the number of insects there at time n, x plus n plus 1 is the number of insects the following year, and they found that this is the equation relating insects one year to the next year. You take the population, the fraction of total, times 1 minus x, and multiply it by some equilibrium constant, r, and that's the number of insects. Now, population reaches an equilibrium if what happens is xn and xn plus 1 are the same. That is, they reach an equilibrium, the same number of insects are there year after year, and the population is in equilibrium. So this growth equation looks for equilibriums. And people wanted to find equilibrium points for different values of r being the driving force. Okay? What are the different equilibrium points for different values of r? To do this, we do what's called a bifurcation diagram. And now let me explain that. No, I'm going to need to have it on the screen here. I have a screen. Here's the television screen, actually. It's a computer screen. Now, each dot, there are 640 dots this way on my computer screen, and there's 480 dots this way on my computer screen. I'm interested right now in using the 480 lines. There's actually 480 lines on my screen. Now what I'm going to do is I'm going to start at r equals 0. I want to know what happens in terms of r, and I'll end at r equals 4, which is the highest I can really go with that equation that we're talking about, the growth. Remember the growth equation, xn plus 1 equals r times xn times 1 minus xm. So r, I'm going to let r go from 0 to 4 in 480 steps, and there'll be a line on the screen on which I can print my answer. My answer is the following. I pick a starting number. Oh, I put so many insects, x0 insects, into the field, and then let them run for 100 years. And then after 100 years, I plot what xn plus 1 is for each successive year for another 100 years. So I start off 100 years, let the insects sit there, reach equilibrium, and then plot where they are the next 100 years. Now, if I'm lucky and there is an equilibrium, what's going to happen is that there will be a point. And that will be the only point that will get plotted. There'll be a blank page on each line. There'll be a blank page except for a point. And that point should be the equilibrium value for the insects population for each of the 100 years, because they're in equilibrium, so it stays there. That's what we expect to find. And they wanted to know, well, what is that equilibrium as a function of r? Maybe it's something like that and whatever. So we want to see what it is. And that's what was asked for, that's what the computer was asked for, and it produced this bifurcation diagram. And that's the bifurcation diagram that came out. Now, wow, something wrong here. When r is 0, it settled down to 0. The insects died. In fact, all the way till r equal 1, the insects died. But then r bigger than 1, in fact, up to r equal 3, there was a unique equilibrium value, just what they wanted to find. When r is 2, say, and you put in this many insects, it will bounce around for a while, and then it will settle down here, and forever and ever it will be there, the equilibrium value for the number of insects. Well, that was very good, but when they got above r equal 3, to here, say, they found, instead of 1 value, they found 2 values. And I said, wait a minute, that's not equilibrium. insects here one year, next year they have this many, then this many, then this many. It bounces around. It's got a period. Well, that explains the 7-year locust. Insects are this number, and then every once in a while they bounce to this number, and then they bounce back to this number, and they bounce back to this number. And so for certain values of R, the population is 2 values in equilibrium rather than 1. And look what happens. As you go even higher, there's a place where those 2 split again. They bifurcate, and you get 4 different values, so that the population growth will be first here, then here, then here, then here, and the insect population is bouncing with a period 4. Well, let's magnify what's going on in here. Magnify this a little so I can see what's happening. So I went down here just before it split up to 4, and I can see that it splits into 4, but I can also see that as you go a little higher in R, it splits into 8. And as you go a little higher in R, it splits, you can see it splits into 16. You can just about see it. Well, what's happening is this bifurcation is continuing on, and for very tiny increases in R, you have doublings. Every tiny increases is a double, 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 until eventually you reach a point where, up here, let's see, where every possible value is possible. In fact, and never returns. Insect growth is just totally random from point to point to point. Every year it's a different insect growth. There seems to be no order in what's going on here. Well, this thing is full of structure. Look at it. This is not accidents. These lines, just let's see if we can't magnify this a little bit more and see something. What's happening is that we have this bifurcation going into places where it seemingly never returns, and then all of a sudden, as you can see here and here and here, here's a good one, it again breaks up to where there's, in this case, a period of 6. It's easy to see that there's 1, 2, 3, 4, 5, 6, and there's only 6 values which the insects could take on. Each year there's a different value, but it's only 6. But just below that, there were infinite number of values. Where there's an infinite number of values, in particular up here, for instance, we call that chaotic behavior. This thing doubles and doubles and doubles until it becomes chaotic, and there's no way, supposedly, of predicting what's going on. Well, wait a minute. What do you mean, no way of predicting? We know that, give me R, all I got to do is take X and multiply it by 1 minus X, and I'll get the next value. I can predict exactly what it's going to be. It's no surprise at all. What the next value is no surprise. There's complete determinism here. It just doesn't happen to repeat, and it doesn't happen to stay stable. There's no equilibrium. That doesn't mean there's no predictability. I can predict if I know this equation. Now, this region, the region where it's supposedly unstable, doesn't look like there's anything happening but a mess, is called chaos. This is the chaotic region. That's chaos. Chaos is when you no longer have stability. You have things bouncing around, supposedly random. And I've been avoiding using the word random because it's not random. I can actually predict the next value. Then why, when you hear chaoticists talking, do they say chaos means you can't predict? Because of chaos, we cannot predict what's going to happen. Because of chaos, we cannot predict what's going to happen. Well, if we didn't know the equations, we wouldn't be able to predict, but that's not why they're saying it. The reason people say that chaos means you can't predict, even though we saw that we could predict in this simple situation, is because of the butterfly effect. Now, this is an interesting concept. Let's say in Ecuador there's a butterfly flapping his wings, or not flapping his wings. He decides whether he's going to flap them or not. If he doesn't flap his wings, we have one set of air conditions. If he does flap his wings, we have a slightly, ever so slightly, different set of air conditions. That little change could be way out there in a 20th decimal place or so. And I have an example here to show you what would happen if there was a slight change in the 8th decimal place. That's all these numbers the computer could handle at this time. So in the 8th, 1, 2, 3, 4, 5, 6, 7, 8, I have 8 3s here and 7 3s and a 4 here. So that represents the air conditions when the butterfly didn't flap his wings and when he did flap his wings in Ecuador. Now, that air situation affects the air next to it, affects the air next to it, affects the air next to it. We have a repetitive situation, just like the growth equation, where one x depended on the x from before it. Anytime you have a situation where the next one depends on the last one, we say we have an iterative situation. Well, in air conditions, we have an iterative situation. The air near Ecuador depends on the air in Ecuador. The air near it depends on it. And there's an iterative situation going on. And here we have Ecuador's weather without the butterfly flapping his wings, Ecuador's weather when the butterfly flaps his wings. And of course, as far as we're concerned, the weather is really what's happening in we're only interested in the gross weather, not in the infinite decimal places. Now, as we go on through time, we go through Chile and Argentina and up through Mexico. And as you can see, the weather is not noticeably different all the way up through. There's not much of an effect of the butterfly. Actually, this is very close to Ecuador, but let's say it's all the way up through Mexico. And then it's going California, and we're in California and in Arizona. And look, wait a minute, look what's happening here. All of a sudden, by the time we get to Arizona, things are a little different. Now we're in Chicago. Now we're coming down. Whoops. We're now in Christiansburg. We're now getting to Blacksburg. Here we are in Blacksburg. Look at that. The weather is completely different. If the butterfly didn't flap his wings, this would be the weather in Blacksburg. Because the butterfly flapped his wings, that's the weather in Blacksburg. The weather in Blacksburg is dependent on whether or not the butterfly flapped his wings or not. Well, how are we to know whether a butterfly in Ecuador is flapping his wings or not? If that butterfly has such a great effect, tremendous effect you saw, on the weather in Blacksburg, then there's no way we can predict the weather in Blacksburg, because we don't know what that butterfly is going to do. And so chaotic people, chaoticists always say, chaos means you can't predict, totally unpredictable. What they really mean is in a very short range, it is predictable. We know exactly what's going to happen in the next time, and a time after that, and a time after that. But the errors in our measurement begin creeping in, and soon they overwhelm us, and there's no longer predictability. And so short-range prediction, yes. Long-range prediction, no, in chaos. Okay? Now, haven't drawn these pretty pictures yet. Let's get to another branch of chaos. We're going to draw some graphics here. We're going to work on graphics. What we're going to do is we have a screen, and there's two coordinates, x and y. That's how we map out our screen. And there's two ways to do it. We can just say x and y and talk about two coordinates, or we could talk about the complex plane. Say this is the complex plane. Mathematicians much prefer having one letter to represent the point than two. You say, oh, this point, that's x comma y. But that's two dimensions. They like one dimension. So they're going to say, okay, z. Z is that point in the complex plane. But z is really x plus y times I, which is the imaginary number, square root of -1. Now, you know there's no such thing as the square root of -1. It's called an imaginary number. And what it does is allow us to plot a point on the plane with one complex number. That complex number has two parts. It has a real part and an imaginary part, which really is no more than what we had before, an x and a y. But at any rate, it makes mathematicians very happy, and it allows us to do arithmetic a little easier. Okay? So the graphic screen is now made up of points in the complex plane. Each point has an x and a y coordinate, and therefore it has a complex value, x plus iy or yi. The iterative function that we're going to work with in this, remember, we always talk about iterative functions in chaos. The iterative relation we're going to work with is that if we start out with a z, the next z is the square of the old z plus a constant. So square, you're at a particular point in the plane. We have ourselves a point, or we have a value of z. The next value of z is the square of that value plus a constant. All right? Now, this relationship diverges. That is, it runs off to infinity. It gets big and big and big. If z ever reaches 2, the absolute value of z ever reaches 2, that means if I have a circle of size 2, anything outside that circle will, of course, be bigger than 2, and the thing will run away to infinity. So if the absolute value of z is 2 or bigger, this thing diverges. And it's interesting to know when it diverges. And in fact, what n is when it diverges is called the escape time. The escape time, and you may have heard that, and people talk about chaos all the time. The escape time is the number of iterations it takes for the z to reach 2, because we know once it reaches 2, it's essentially gone. So we call that the escape time. I'm going to use this relationship, and z of n plus 1 equals zn squared plus a constant, this is a complex constant, to draw pictures on my computer screen. Now, what I'm going to do in this relation is I'm going to start with the first one, the initial z of 0, and c, the value that I'm going to add each time, is going to be the value of the point. So I have a screen. Essentially, I'm going to start with 0 in the middle, and plus or minus 1 here, and plus or minus 1.5 here, something like that, maybe 1.2, so that I have a screen that big, and each point is a complex number with those coordinates. And I'll use that as, for each point, there's many thousands of points, take one point at a time, and that's the value of c, the value of z at that point. The z in this equation is 0. Z0 is 0. But the very first time I run this through, if z0 is 0, then z1 is equal to c is equal to c. Because 0 squared is 0 plus c is c. And z2 is equal to c squared plus c. So this is a complicated relationship I have here, especially since the c's are complex numbers. They're the point, this point. Well, this point either diverges or it doesn't. If it doesn't diverge, then I don't care about it. If it diverges, then it's part of what I call the Mandelbrot set. Not just me, everyone calls it the Mandelbrot set. You've heard of the Mandelbrot set. You'll see a picture of it in a moment. So if this goes to infinity, it's part of the Mandelbrot set. And I'm interested in the escape time. How long does it take to go to infinity? Does it go on the very first iteration? Does it take 2? Does it take 3? Does it take 10? Does it take 15? Draw me a picture where they go in one iteration. Draw me another. I would think, if you were doing that you'd end up with something like this, where the farther ones go in one iteration. In here it takes 2, and then in here it takes 3, and then more. And when you get real close to the center, it doesn't diverge at all because they're too small. That's what one would expect. However, that's not what happened. Now remember, the c in the equation is the point in the plane, and I'm going to plot a color representing the escape time. Blue means it escapes 1 in one iteration. I think then comes red and green or whatever. You'll see the sequence of colors. But if it escapes quickly, that's blue. If it escapes after 1 iteration, that's a different color. 2 iterations, another color. And we would expect to have something like that. Let's see the first slide. That is the Mandelbrot set. The very center, it's a sort of a dark blue there. It should have been made black, but dark blue is the place where it converges. In fact, you see many little places where it converges, little circles after circles. And the outside, look at the very extremes of the picture. That's blue. That's where things diverge very quickly. By the very first iteration, it's bigger than 2. The next color is green. In 2 iterations, it will converge for all points there. Third one is the light blue, then comes red, then comes violet, And you see, as we go in further and further, closer to the place where it doesn't converge, there are many, many, many colors right next to each other. Many colors. Chaotic. It's chaotic because it's not circles, it's not smooth areas. There are places where you converge in 15 and 20, and they're occurring right in between those places. There are places where you don't converge at all. Now notice the circles on the edge of circles, and there are other circles on the edge of those circles. And what that is self-similarity. What we have here, could shut that off now. What we have here is a fractal. This is a fractal. There are circles, and there are circles in circles. Let me draw a picture of a circle here, and a circle there, and a circle here. And in these circles, there are other circles, and in those circles, there are other circles. And those are the edges of the Mandelbrot set. The edges right here is where it's diverging. And sometimes, if you magnify this, you'll see places where it diverges and places where it converges right next to each other. There's no order. It's totally chaotic in there. Now, I could magnify it and show you what's going on, but I'm not. I'm going to go to the very next topic because the pictures are even prettier. And that's called Julia sets. Julia sets are very similar. However, the formula is the same. We talked about this formula. Zn plus 1 equals Zn squared plus a constant. Only now the Z0 is the point on the screen and not 0. Z0 is the starting point, and C is a constant. Now there are millions of Julias. There's only one Mandelbrot set, but there's millions of Julia sets, and that's because there are millions of constants that you can use. The most interesting constants are those that are on the edge of the Mandelbrot set. Remember the Mandelbrot set? Well, those on the very edge of the Mandelbrot set are the interesting constants. So we're going to pick one of those points on the edge of the Mandelbrot set, make that the constant, and then we'll provide a Julia set, which says for every point in the plane, again, we'll go 1 minus 1 plus 1.5 minus 1.5. For every point in the plane, we'll start x0 at that point, and then we'll square that point and add c to it. Then we'll take what we had, the new one, square it, and add c to it again. And the c will always be a constant for each picture. And the c I'm going to pick for this one. Let's have the screen. Oops. I want to pick it out. Can you see in the upper corner there's a square? Right in the upper part, there's a square there. That center of that square is the point I'm going to use for the constant. The value, the complex value in the center of that square is the point I'm going to use for the value of the constant for the Julia set. Now, I can move that square around anywhere I want it on the screen, and I'd have a different constant. But I'm picking that one. That's the Julia set that I get from that center point in the Mandelbrot set, that little point, and using, for each point on the screen, the point on the screen is the constant Z0. And I square it, and then I add the constant coming from the Mandelbrot set to it. Now, look at the little square there. I'm going to show you some self-similarity. I'm going to magnify that square. I get a little something, tentacle. Now you see the square? I'm going to magnify that square up in the corner there. I'm going to magnify that square. It's in a similar place, but I get a tentacle. I'm going to magnify, there's another little square, and I get another tentacle. Self-similarity. These things all look similar. I'm taking little things and I'm magnifying them, and they all look similar. There's another little square up in the top. You can barely see that one. I'm going to magnify that one. And there's another tentacle with another square in it. I'm going to magnify that one. And there's another tentacle. I've skipped a few. I've gone through these things, magnifying. There's another square and another tentacle. So I'm magnifying and magnifying and magnifying and magnifying, and they all look alike. Very similar, very, very similar. I think that may be it. Let's take one more. Okay. Look at that picture. I got tentacles. Okay, let's come back. Now, I kept magnifying, and I skipped a few magnifications. And no matter how deep I go, I got chaos, because right next to points very close to each other are behaving quite differently. Escape times are different, some of them not converging, some are diverging, and when they diverge, they don't behave in a similar way. Points right next to each other are behaving differently. Now, how much of a magnification was that? I mean, if it's just a little magnification, that doesn't mean points are behaving differently. Well, let me explain the magnification. Remember the original Julia set? I've expanded that, so it's very, very large because I'm now looking at a little tentacle in part of that. How big do you think that original Julia set is now that we've had this on the screen? If you take your screen and that picture was on it, the original Julia set would take up the orbit of Pluto. That's how large it would be. So we have looked at a little itty-bitty, and my God, that is little itty-bitty, isn't it? Little itty-bitty piece of the whole world. And we're looking at that, and we still see points next to one another which behave chaotically, behave differently, behave in a way we can hardly predict. That's chaos. That's chaos. No matter how deep you go, you get chaos. Let's get the pictures back. I want to show you, I want to end with some pretty stuff, some other Julia sets. That's the Julia set we got from that point. If you take a different point from the Mandelbrot set, you get different Julia sets. Here's another Julia set. And here's a different point, similar but a different Julia set. Here's another Julia set, a different point on the Mandelbrot set give another Julia. This, by the way, these are magnifications of the Julia set, not the set itself. That's a magnification, too, of another Julia set, a different place. And that's another one. Interesting, aren't they? Very colorful. Points next to one another behave differently. And there's another one. I call that my amoeba slide. There's an interesting one. Here's my favorite. I like that one. It sort of shows what Julia sets are all about. Okay, I think that's it. You can shut it off. Now, I promised you pretty pictures, and I gave them to you. And randomness, how does that come in? Well, people mistake chaos for random. In fact, it is random, because random means we can't predict. Chaos means we can't predict. The difference between random and chaos is that chaos can be predicted for a short period of time. There are certain regions that aren't chaotic. They behave well. And then there are regions where it's chaotic and we can't predict for very long at all. And in this pictures, we can't predict down. When we get down to the real bumpy places, we can't predict what's going on at all. So it behaves randomly. It behaves as though these were random points. Okay? Have a good one.